Hi, I'm David Williams, a member of the Oxford Robotics Institute, and I'll be presenting my paper named Fool Me Once, Robust Selective Segmentation via Out-of-Distribution Detection with Contrastive Learning. In this work, we concern ourselves with the task of semantic segmentation, whereby we define a set of classes we are interested in, and then we seek to assign each pixel in a scene to one of these predefined classes. But as every pixel doesn't necessarily correspond to one of these predefined classes, we also need to define the so-called void class to account for this. A neural network can then be trained in a supervised manner by using a set of images with corresponding pixel-wise labels. Once the network is trained and we're happy with the performance of the network on a withheld test set, which broadly contains images drawn from the same underlying distribution as the training data, we might then consider deploying the model. But at this point, we're no longer in control of how the data is distributed, which we might refer to as open set conditions. And then the model is asked to assign classes to objects that do not fall neatly into these predefined classes, and they also look nothing like what we labeled as void in the training set. This distributional mismatch between the training data and the data seen after deployment is referred to as distributional shift, and it's a problem because it often undetectably leads to an error rate that's higher than that seen in the training and the test set, which is naturally a cause for concern. For our segmentation case, this is broadly caused by objects of unknown class, or of objects of known class but unknown appearance. Preventing failures of this form is included as part of the new international standard for road vehicles. It requires that the safety of the intended functionality must be guaranteed in the absence of a fault. So this promotes the idea generally that autonomous systems must be designed such that system failure can be detected even when no obvious fault occurs, as seen in this case where distributional shift causes failure without any changes to software or hardware. Classification and segmentation networks naturally output a form of uncertainty in terms of the entropy of the categorical distribution, relating to how similar the classification scores are for each class. Unfortunately, this measure can be poorly calibrated in the sense that it correlates poorly with the achieved accuracy of the network. This effect is particularly pronounced on out-of-distribution inputs and of course on adversarial examples. There are a number of different techniques that can be used to overcome the lack of native capability for introspection of segmentation networks, including epistemic uncertainty estimation, deep generative models, softmax calibration, and other novelty and anomaly detection techniques. On the whole, these methods only tend to use in-distribution data to learn the representation, and then that gets used for out-of-distribution detection. This can lead to a scenario sometimes known as feature collapse, whereby in-distribution and out-of-distribution data look identical in feature space. This naturally means that many out-of-distribution inputs cannot be distinguished from in-distribution inputs, regardless of how the uncertainty is expressed in the network. This then leads us to our submitted paper. So this work is named Fool Me Once, after the famous expression, fool me once, shame on you, fool me twice, shame on me, to allude to the idea that if we fool a network with unknown classes during training, it's then given the opportunity not to be fooled after deployment. More concretely, we aim to train a network to simultaneously perform semantic segmentation and pixel-wise out-of-distribution detection. And in doing so, we can then reject the segmentation of pixels deemed out of distribution, with the idea that it's highly likely that proposed segmentation in these regions is wrong. And this is what we refer to as selective segmentation. As previously stated, what is considered out of distribution is the set of all natural images that contain objects that do not belong to one of the predefined classes, or any object that does but looks significantly different. So the set of out of distribution images is clearly far, far larger than the set of training images. Nonetheless, in this work, we choose to expose the network to some of this, and we approximate this set by using ImageNet. The idea is that even though we can't learn a semantic understanding of this enormous set of out-of-distribution images, we can use it to learn more robust features from the training data that are not found in the out-of-distribution data, such that this so-called feature collapse does not occur. Despite the large increase in data used overall, also the labeling effort required does not increase at all, as all the data in ImageNet is simply assigned the label out-of-distribution. Here we have a quick visualization of the difference between the two datasets used to train the segmentation networks. Some of these out-of-distribution objects are unlike anything seen in driving data, However, some could be easily mistaken for objects seen in road scenes by a network that's only been trained on a very narrow view of the world, i.e. only on the driving data. For example, metallic objects could be mistaken for a body of a car, or objects with strong red features could be mistaken for car headlights or traffic lights. These moments of confusion can then be used to improve the network's understanding of the objects seen in the driving data. Out-of-distribution data can be leveraged by using the contrastive loss function in conjunction with the standard supervised cross-entropy loss. Our loss function builds on the loss function seen in works such as SimClear and MoCo, which have been very successful at learning representations of images in a fully self-supervised manner, and this loss is often referred to as the info NCE loss. The first step is to compute the cosine similarity between all features in a batch. And then features from in-distribution pixels are encouraged to be as similar as possible, which is the numerator of the loss function. And then features from out-of-distribution pixels are encouraged to be as dissimilar to the in-distribution features as possible. And then if we use the info NCE loss directly, the features belonging to the out-of-distribution class would also be forced together. However, we don't enforce this, as that will be trying to compress all out-of-distribution features into a single cluster and feature space, which either won't work or lead to overfitting due to the sheer size and diversity of this out-of-distribution set. And then finally, both the contrastive loss and the supervised loss are backpropagated together and used to update the weights in one step. Once the encoder has been trained to produce features for both out-of-distribution detection and segmentation, a decoder is then trained to produce the final classification of whether a given pixel is in or out of distribution. For this, it's trained with the same data as before and with a binary cross-entropy loss function. As we're trying to achieve pixel-wise out-of-distribution detection, it intuitively makes sense to combine the datasets also in a pixel-wise manner. But detecting one image cropped into another image is fairly trivial due to the inevitably large image gradients by the edge of the crop. And in this naive method of cropping out-of-distribution images into in-distribution images, the problem can be solved fairly trivial with no semantic information learned. We therefore opt to perform each combination of cropping in distribution into out into in into in, and then also out into out. Thus, if the network has detected a crop, it also has to understand the semantic content of the crop before it makes any assertions about where the crop has actually come from. As ImageNet is also much more colourful than driving data, which on the whole is very grey, we also then match the mean hue and value in HSV space between the crop and also the pixels it replaces in the background. And this removes colour as a strong discriminative feature between the two datasets. And again, it removes the possibility of a trivial solution to the problem. In order to test our trained system, we opt for the wild dash dataset. It contains 4,000 pixel-wise labelled real-world images of driving scenes taken from dash cams all over the world. As can be seen, it contains many objects considered out of distribution and so is ideal for testing the limits of a network performing segmentation. Testing on real-world data in this way is a much more difficult task than is often seen in out-of-distribution detection literature, when the task is often to mix in one dataset with another, and then in testing, the network has to separate out the two datasets of images, or alternatively, you synthetically add out-of-distribution objects to real-world images. Our objective is to have the network segment as much of the wild dash dataset as possible, and then it has to reject its segmentations of objects for which it justifiably is uncertain. We report these results by plotting mean intersection over union versus coverage. Coverage is the percentage of pixels the network feels confident in segmenting, and mean intersection over union is our measure of segmentation accuracy, and it's calculated only on these regions where the network is confident. We traverse the coverage axis by changing the threshold on the classification of whether a pixel is in or out of distribution. We test variants of the proposed method with different forms of data augmentation and other similar loss functions seen in literature. Additionally, we include a baseline, which is a segmentation network trained on in-distribution data alone, and it uses softmax scores as a measure of uncertainty. As you can see, when tested on the most challenging data in the wild dash dataset, the network trained with both our additional contrastive loss and our data augmentation performs the best, and this is the line seen in pink. We say this because it achieves a higher mean intersection over union over a range of coverages, and particularly around 50%. This means that it's able to achieve a reasonable mean intersection over union around 40% on about half the pixels in the test dataset, while rejecting the other half as they are deemed out of distribution. Here we can see some qualitative results from testing on the wild dash dataset. The network is rejecting its segmentation of uncommon signage, a cast of chopped wood, and some unfamiliar street art, each of which are segmented incorrectly as they are considered unusual with respect to the labelled in-distribution data. The first example suggests that the network can also reject objects which belong to one of the predefined known classes but are considered out of distribution due to their unusual appearance. This suggests the network has a general sense of what it recognises and has good semantic features for, and also what it does not. Thanks very much for listening, and feel free to get in touch.